Hey, how's it going? Thanks so much for coming to our talk, which is what the heck is Gevent? Next slide. So yeah, my name is Roy. I'm a principal tech lead manager here at Lyft. I support the developer platform team. As mentioned, we own a lot of the tools that engineers use to build APIs and otherwise build Lyft. And Shiv, you want to go introduce yourself?
Yeah, my name is Shiv Toolsidass. I work as a software engineer at Lyft, and I work on the bikes and scooters team over here.
Cool. Yeah, so today we're going to be talking about Gevent. You may have heard about Gevent before. It's, as Shiv will talk about more, it's kind of magical pixie dust you sprinkle in your code to automatically make it have much higher throughput. But with that great power comes some downside. There can be some correctness problems you run into. There can be some performance problems you run into. And then Shiv's going to talk through how we took some of these learnings about Gevent as a whole and applied them to improve the business here at Lyft. And then we'll talk about some takeaways and end with the Q&A. But with that, we'll hand over to Shiv for our intro to Gevent. Take it away, Shiv.
Awesome. Thanks, Roy. So let's get into what Gevent is. Gevent is a coroutine-based cooperative multitasking framework. That's a mouthful, but don't worry, we'll explain what each of these terms means in a bit. So why does Gevent matter so much to Lyft, and why are we giving this talk to you today? The bulk of Lyft's Python microservices are backed by Gevent. When you open up your app and request a ride, our Python web servers are able to schedule requests thanks to Gevent. Understanding its intricacies has allowed us to scale Python really well in production. And why should Gevent matter to you? If you leverage an async framework or language that uses an event loop like Node.js, these learnings are going to be really useful to you. And if you're encountering challenges scaling your services, they're especially relevant. Like Roy said, Gevent works like magical pixie dust. You write these 2 lines of code, and your service is able to 10x its throughput and cooperatively multitask its workloads. However, this power comes at a cost, and we're going to explore that during this talk. To understand how Gevent works, let's look at a scaling problem that Lyft might encounter while matching passengers and drivers. Let's hop on over to a Jupyter notebook to look at some code examples. Awesome. So let's say that Lyft matches passengers and drivers by matching passengers with the driver closest to them. So let's say we have a couple of classes that model ETAs, user, drivers, and passengers. Now let's say we have 2 drivers, Shiv and Roy, and we have 2 passengers, Alice and Bob, and we're trying to match Alice and Bob with drivers in the Lyft platform. These requests to match Alice and Bob are separate web requests, and let's say we match them one after another synchronously. This takes about 2 seconds. Now, this is fine when Lyft's small, but let's say we start experiencing hypergrowth and lots of drivers and passengers on our platform. This doesn't scale very well, and our users are unhappy because it takes so long to be matched with the driver. So how do we fix this? Let's add some concurrency. We import this library called Gevent, which we just talked about. And don't worry about these 2 lines, they'll make sense in a bit. We also have to spin up a separate subshell because Gevent messes up our Jupyter notebook and import our classes again. So you can see that we have the exact same code, except that we modified this 1 line and added a gevent.joinAll and spawned up several greenlets to handle this workload and make it concurrent. And amazingly, it's cut down our wall time in half. So just to recap, very few code changes, really neat. Now let's compare that with another popular framework called async.io. In this example, you can see we had to change our code a fair bit. We had to add in these async definitions, we had to add in a wait, and overall, a couple of more changes than just using Gevent. And when setting up this example, we actually fumbled quite a bit, and it took us a while to come up with it. So it does add a bit of complexity to your code. It's not as elegant as Gevent. So let's get back to digging into what Gevent's all about. So earlier we told you that Gevent is a coroutine-based cooperative multitasking framework. Let's break down what that means. In the word coroutine, co stands for cooperative, and routine stands for function. Coroutines are functions that cooperate with each other. Let's first take a look at some functions that are not cooperative. In the example here, when print numbers calls into get numbers, print numbers can continue until get numbers finishes and returns to where it was called. the control remains with get numbers until it executes completely, and only then can the control be returned back to print numbers. Back to coroutines. So what are coroutines? Coroutines are functions where the control is transferred from one function to the other in a way that the exit point from the first function and the entry point to the second function are remembered. And this happens without changing the context. So each function remembers where it left off execution and where it should resume from. In the example in the slide, control is transferred from print numbers to get numbers. And when the yield function is encountered in get numbers, the current state of the function is saved and control is returned back to print numbers. On the second iteration of the for loop in print numbers, control is returned to get numbers. So as you can see, we can leverage this concept to pass around values between functions in the middle of their execution without breaking away from the context of each function. This notion of yielding control from one function to the other is the building block of concurrency in Gevent. So in Gevent, a coroutine is called a greenlet, or also known as a green thread. But keep in mind that a coroutine is not a thread. Earlier, we said that Gevent is a cooperative multitasking framework. What does that mean? Cooperative multitasking is a style of multitasking where the operating system never initiates a context switch from one running process to another. That style of multitasking where the OS initiates a context switch is called preemptive multitasking. The operating system understands priorities and how much time each task is run for, and it can interrupt processes to allow another one to run. In cooperative multitasking, on the other hand, processes voluntarily yield control to each other when idle or blocked. In this form of multitasking, programs must cooperate for scheduling to work. The image on the right over here is Windows 3.1, which used to rely on cooperative multitasking to allow multiple applications to be run at the same time on a computer with one core. The other thing to know about Gevent is that it uses this concept called monkey patching to modify the runtime behavior of standard and third-party libraries so that they can be cooperative. In the example in this slide, we monkey patch time sleep function. When we run this program, it prints out should have slept 10 seconds instead of actually sleeping 10 seconds. In Gevent, monkey patching is the first thing a process needs to do. Otherwise, libraries are going to perform real blocking implementations, which won't be cooperative. Monkey patching is generally considered to be a bad practice because it can lead to bugs that are hard to understand. For example, if the underlying library changes, the monkey patch needs to be updated as well, and one might forget to do this. So let's tie everything together we've talked about so far with an example. Monkey patching, in this example, makes time.sleep that's invoked in the sendstat function cooperative. Instead of blocking the CPU, it yields control for at least the sleep time. All the functions in this example are cooperative, otherwise known as coroutines. Control is yielded from doThing to sendstat, back to doThing, which yields control back to doThings. I'm going to hand it back to Roy to talk about correctness in Gevent.
Cool. Thanks, Shiv. Really appreciate your overview. And so with that, we're going to dive into some more code and talk about some of the nuances of Gevent. So as Shiv mentioned, Gevent is a really useful library for changing code that was written in a synchronous manner and automatically making it asynchronous. But this can come with some of the traditional problems that come along with thread-based programming. So if you've ever worked with Java or things like that. So we will go through some of the examples here and some of the problems and how we're going to fix them. So for this first example, we're going to imagine that we're building a bank, like no fancy cryptocurrency, just a traditional in-memory bank database. So we have a database here that just maps strings to integers, which is just the name of the account, to the balance. We can list the accounts. We can send money between accounts. We have some useful debugging code here that we'll use later. And we have this function here, compute new balances, which is what we use to decide what the new balances should be. It takes in the old balances, the amount to transfer, and creates the new balances. So you can see when we send money, we just compute the new balances, and then we assign those values in the database. Pretty straightforward. So I have my code here. Great, it's running. You can write some unit tests for this code. If I send $10 from Roy to Jack, Roy should have $90 and Jack should have 110 at the end of the day, assuming everyone starts with 100. I run my test, which is great. Now I'm going to introduce a new function here called send money around. Now this function is just going to send money in a loop. So of the 3 people, Roy will send money to Jack, Jack will send money to Nick, and Nick will send money back to Roy. And so at the end of the day, everyone should have the same exact amount of money in their bank account. And so again, we can write this code and write another unit test, and our test pass. And because and to simulate web traffic with a Gevent-based system, I'm going to be spawning a bunch of greenlets. They're going to start at random times, so call send around money. And we run this, and it's great. With those 100 requests that are sending around money, at the end of the day, everyone winds up with an equal amount of money in their bank account. So I'm feeling pretty good about this. Now, let's say we're getting ready to go to production. We have this Gevent-based system, and I send this for code review to Shiv. Shiv, being the stickler for correctness that he is and reliability, he says, Roy, you got to add some logging to this code. How are we going to know how much money is being sent around? And so I say, you know what, Shiv, you're right. We're going to add a function here called stats incur amount, which is going to just increment some counter for the total amount of money. And we figure compute new balances is the right place to put this code in. And this feels pretty low risk, right? I'm not going to try to look at Discord at the same time, but put in chat if you think this is risky or this is safe change to make. It feels pretty safe to me. Like what's wrong with observability? Nothing can go wrong here. So we're going to add this code in. Think as to what could be breaking here. We're going to run a unit test though, just to make sure everything's okay. And great, our unit tests still pass. So let's go ahead and put this in production. And let's see what happens. All right, so something's gone wrong here. Jack has $120 at the end of this. Nick has $130 at the end of this. Let's just try it again. Oh, wow. Now Nick is really angry because he only has $40 left. I'm super happy because I've got triple the amount of money. What could be happening here though? Like this doesn't make sense. How could just adding a stat call create all of this mayhem inside of our code? So luckily we did add that debugging code in earlier. So we're going to go ahead and use that. And all this code, by the way, we wrote a blog post about Gevent and all this code is in there. So if you want to download it and play with it and work with the problems there, you can try it for yourself. Okay, so this logging code will spit out changed if the amount of money changed between when the transaction started and when the transaction finished. And so let's look at this example here of thread 93 sending money from Nick to Roy. And so at the start, before we compute the new balances, Roy is 110, Jack has 110, and Nick has 90. But now afterwards, Roy has 110, Jack has 110, and Roy has 100, Jack has 100, and Nick has 100. So what has happened is the balances have changed out from underneath me as I was starting to run this code. And you can see where this happened right here. So because I added in the opportunity to context switch, what has happened is that we context switched to another thread. When I started to compute the new balances, I switched to 57 and finished that up. And I started 63 to compute those new balances there. But 57 changed the balances out from underneath me. Before, there was no opportunity to context switch, but now there is one. And that's what's creating this mayhem. That's what's creating this problem. And so traditionally, you think of this as something called a critical section, or a piece of code where you can't have any context switching. And so we're going to talk about 2 ways you can potentially fix this inside of Gevent. The first is to avoid the context switch, to avoid the critical section altogether. So instead, we may do what banks usually do. Banks very rarely update the actual account balances. They keep everything in a ledger. One of my first mentors told me that accountants don't use erasers. If they accidentally send too much money, they don't update the account balance, they do a reconciliation transaction. And so that's what we're going to do here. Instead, we're going to accrue transactions to a ledger. And then when we read the database, we will replay all of those transactions to get the current state of the database. This is obviously much more expensive, but should be a lot safer. Great. And so now I've got my concurrent system running and I don't have any of this nonsense of tripling my money. Another way, this is also one place where async IO actually can add some value. So if I were instead to try to solve this problem with async IO, I'm just gonna go back to the old state of the code. So with async IO, one of the problems with this code here is that I have no indication that this function, stat sync or amount, is going to make a network call. Even if I want to try to avoid context switches and keep this all running at the same time, I can't really enforce that. In async IO, because you're adding in these new keywords, you can actually enforce that, and the caller gets some indication that the code is going to context switch. So if I were to use async IO instead, I'm gonna get an error when I try to await from a regular function. So I have to mark that function as async. And then when I wait here, I also get the same error. So usefully, I get more signal as someone using this code that, hey, this code is going to context switch. And so now actually I know this is good signal to me as an engineer that, hey, actually I can yield here when I'm calling the stat sync amount. And so actually I could wind up with incorrect balances here. Going back to the old code though, another potential solution to avoiding context switches is actually Gevent has some support for this. So Gevent built in has a function called assert switches, which is a way inside of test cases to assert that a chunk of code will context switch. We obviously want the opposite of that, but we can massage the test case into being what we want. So if we take our old bank, so we assert switches and then we fail if the exception doesn't throw. So we take our old test case and we fail because we were context switching. If I go back to the code and I remove the stats call, I'm gonna pass. Or if I change to running a safe bank, my test is gonna pass again. And so now I have a few options for how we can think about solving some of these concurrency problems. Switching gears to performance. Again, Gevent, like you're using Gevent to improve the performance of your code. And so it may be surprising to hear that can actually cause a lot of performance problems. So as Shiv had mentioned, Gevent is great for parallelizing code. We can take some code that's fetching a bunch of resources serially and now automatically make them fetch in parallel. For this example, though, we're going to be using something akin to like a web server. Now, most web requests do a mix of CPU work and IO work. So we have a function here that's at the bottom. We're going to be running a series of benchmarks. I'm not going to actually run them here. I'm just going to show the output for in the sake of time. But we can take in the work time, the network time, and the number of green threads that are running. And so you can imagine this setting here being roughly equivalent to this, where we're going to do 5 milliseconds of compute work, 55 milliseconds of network work, and then we're going to be off to the races. And then we're going to output a bunch of statistics here. So we're going to run this benchmark here for 5 milliseconds and 5 milliseconds of CPU work, 55 milliseconds of network with 1 green thread. And we get what we would expect. We have a really tight response time. Everything's centered around 60 milliseconds. P50, P99 are really tight. We have histogram here. But the challenge that we have is this number here. The CPU utilization is at 8%, and this is as high as we can go. And we're only at 16 requests per second. So let's see if we can do any better. So now we are going to quintuple the number of green threads. And lo and behold, we're actually still doing pretty good. We did successfully almost quintupled our RPS, and we've vastly improved our CPU utilization. Also, simultaneously, we haven't really negatively impacted our request time distribution. We're still having that pretty tight 61 milliseconds to 63 millisecond response time. So this seems pretty good. And so let's think about what's happening here. So what's effectively happening is that request 7 is doing some CPU work going to the network. But then when it goes to the network, request 33 comes in and it uses the CPU. And then when it goes to the network, request 2 comes in. And by the time request 7 is done, it's ready to execute. And so this will be my next question to the chat. Feel free to add some thoughts in here. If 5 green threads is good, 50 green threads has to be better, right? Does everyone agree with me? So let's see what happens here. We can actually run this one. This one should only take 10 milliseconds. So take this 10 seconds to think about what should happen here. Is this going to be better or worse than our previous results? And so the good news is we did dramatically increase our CPU utilization. We're at 95%. We did increase our throughput. We're at almost 12x the throughput improvements. But this looks real bad. Our response time distribution, our P50 has gone to 180 milliseconds. Our P99 has gotten to 229 milliseconds. Like this is our histogram. You notice there's some chunking here. We can talk about that in Q&A as to why that happens. But how could this be? How could we have a 60 millisecond request take 180 milliseconds? Luckily, we do have some instrumentation in this benchmark as well that we can go through. So we have an option here to print out to print some details. And so we're going to print the longest request. There's some different settings here, but it's the rough same idea. So we have request 3 here as our longest running request. It starts running. It does this 25 milliseconds of CPU work, and then it schedules its network work that's supposed to take 150 milliseconds. Then request 4 runs, then request 0 runs, then request 5, then 1, then 2, then 6, then 7, and then finally we're back to 3. And this is the really interesting part here. That 150 millisecond network request that spent 150 milliseconds on the wire actually took 225 milliseconds. And what's happening here is we have that same pattern of, we do some CPU work and we switch to the network. But now about midway through request 8, request 7 is ready, but it can't run because it hasn't been scheduled yet. So 11 runs, 33 runs, 6 runs, and then we're back to 7. And so now all this additional time is adding to my latency, really harming the user experience. Of course, because this is a Jupyter notebook, we can use some pattern. We can run this benchmark over and over again and see some patterns. And so we see that for this benchmark, for these settings of 5 milliseconds of CPU work, 55 of network work, we see we asymptote to about 12, that we are never able to get more than a 12x throughput increase. And if you're familiar with any operational research, this probably reminds you of Amdahl's law. Amdahl's law roughly states that the maximum speed up you can expect is 1 over the percentage of the work that's parallelizable. So if you have something that's 50% parallelizable, you can only ever get a 2x speed up. If you have something that's 95% parallelizable, you can only get a 20x speed up. Now, this can be applied to Gevent because this can allow us to think about what is that maximum amount of concurrency that we want? What is the maximum number of greenlets that we want? It's roughly that ratio of CPU work to network work. And to show an example of that, if we are to plot the amount of the response time versus the number of green threads, we see things are roughly steady until we get to 11 green threads, maybe even before then. But then after we go past that, the response times just steadily increase. And so the main takeaway here is that yes, Gevent is great. There are limitations to how much parallelism you want to throw at a process though. And on the blog post, you can find a lot more details of how to better optimize your setup here. And with that, I'll switch over to Shiv to talk about how we use this to solve real business problems.
Awesome. Thanks, Rory. Perfect. Are folks able to see my slides?
You have speaker notes up.
Okay.
Your speaker notes are up.
Oh, gotcha. Let me just modify this 1 sec. Are my speaker notes still up here? Okay, awesome. So in 2020, Lyft had launched a feature allowing users to compare bike and scooter modes against rideshare and transit modes. The goal of this product was to provide users with all the information they need to plan a bike or scooter journey, including ETA, routing, and pricing. After releasing this feature to our users, we noticed a glaring problem in the user experience. Bike and scooter modes would flicker in and out. Before we go further, there's a bit of terminology that I want to introduce. We're going to use the term offer to represent a Lyft mode along with all of its metadata, such as ETA and price. When you enter an origin and destination into your Lyft app, your mobile device pulls Lyft's backend to request a list of offers, like bikes, scooters, Lyft, and Lyft XL. Back to the problem we were encountering. According to our success rates, about 0.5% of requests were failing. 2.5 nines of reliability isn't great for one of the highest value user experiences in the Lyft app. The obvious suspect for these request failures was timeouts. And so we dug into our P95 latency graphs. We found these metrics to be consistently below 450 milliseconds in all of our markets, which wasn't so bad because it was below the configured timeout threshold of 500 milliseconds. However, our P99s in some markets were as bad as 1 second, which was twice our P95 latency. And our P999s were an astonishing 1.5 seconds, which was 3x our P95 latency. So to understand what was going on behind the scenes, let's dig into the architecture powering bike and scooter modes in the Lyft app. Mobile devices pull a Go service called offer service every 5 seconds with the user's origin and destination to request a list of offers. Offer service constructs each mode in parallel And to construct a bike and scooter mode, offer service calls in a pricing service, which is a Python service. We impose a 500 millisecond constraint on the generation of each mode. If any mode doesn't return within 500 milliseconds, it's going to be dropped from the list of offers. So at this point, you may have guessed what was causing the flickering of bike and scooter offers. On the first poll, LBS modes were bike and scooter modes were returned, but on the second poll, they weren't. Alternatively, the first poll returns no results, but the second poll does. For the first case, you may be wondering, why don't you cache these modes? Unfortunately, this feature wasn't available in our platform at the time for various reasons, so it wasn't something we could do. So we decided to dig in a little bit into our metrics, and we found that the bottleneck for this high request latency was the call to pricing service. Pricing service is a fairly large Python microservice that houses hundreds of different endpoints which are a mix of CPU and IO heavy. We had now finally narrowed down the offending call, and so this was a pretty useful exercise. Now, this endpoint in the pricing service was calling into roughly 6 different upstream microservices in order to do things like computing the route, the ETA, and the price. And so we decided to instrument each of these RPCs with the timer decorator in Python and monitored our charts. However, this didn't prove to be so useful. So the next thing we try to do is employ distributed tracing. At Lyft, we use distributed tracing to track the lifecycle of a request across various microservices. This provides you with pretty detailed insights on where each request spends its time. And we noticed that requests to upstream services were being queued up and were sitting idle for a long time, just waiting to be scheduled. This was a really useful exercise for us because it allowed us to confirm that requests were being kept waiting for a long time, which pointed to a web server scheduling problem. And so we decided to dig deeper. We compared our application and networking latencies for all upstream service calls inside pricing service. And we noticed a pretty major oddity while doing this. Our service networking mesh that orchestrates calls between microservices was reporting that calls from pricing service to upstream services were taking around 15 milliseconds. However, pricing services application measured latency was on the order of 50 milliseconds, which is a 3x difference. This was a pretty useful exercise, and it had pointed us once again in the direction of inefficiencies in our request scheduling and pricing service. Now, why was all this happening? It all goes back to what Roy called out in our performance section. Because our service pricing service had a mix of CPU and IO workloads, our CPU intensive requests were effectively blocking our bike and scooter pricing requests from being scheduled by Gevent's event loop. Amazing. At this point, we had discovered our root cause, and it was time to fix it. And so the first thing we tried to do is move our endpoint to a dedicated set of pricing service hosts that would exclusively run offer service pricing requests. By moving this endpoint to these dedicated hosts, we were going to get dedicated G-Unicorn processes that didn't need to contend anymore with CPU-heavy requests from other RPCs. And it didn't have to contend to be scheduled anymore. The results were exactly what we were hoping for. Our timeouts stopped immediately, our flickering stopped immediately, and our success rate went up from 2.5 nines to 4.5 nines. And this was exactly the silver bullet that we were hoping for all along. So our takeaways for you from this talk are that we really recommend understanding how Gevent works under the hood. It's helped us a ton, and we know it'll help you as well. Understand the correctness pitfalls that you might encounter, like the ones Roy called out with the SafeBank example. Understand the performance pitfalls that can occur when combining IO and CPU workloads. And also, if you're interested in digging into latencies for requests, distributed tracing is a really, really useful tool. And if nothing else works, try isolating your workloads. Awesome. That's all we had. Thank you so much for coming out for our talk.